Hi everyone, it's Mr. Denny. Today what we're going to do is look at projectile motion. Now projectile motion is the path an object takes when it is basically launched through the air. And we call this type of object a projectile. Technically a projectile, once it's launched, has no forces on it. So for example, a cannonball would be a projectile because once it's launched, the only thing pushing on it is gravity and its own momentum, and like a rocket or something would not be a projectile because it continues to burn fuel and accelerate and have force from its own exhaust as it's moving. All right, so a couple of things before we get started here. First and most importantly, this guy here, this is Fearless Fred who knows no fear. Fearless Fred will go through a lot of things today. We're also going to learn a couple of terms. So speed is the distance an object travels in a unit of time. So we could say like 10 feet per second. It's a distance divided by time. 40 miles per hour, a distance 40 miles divided by hour. Velocity is the same thing, but with a direction. So if you said 10 feet per second east or 40 miles per hour up, that would be a velocity. You have to have a direction. For those of you in physics, speed is a scalar unit and velocity is a vector unit. Acceleration is a change in velocity over a certain period of time. So if you go from 20 feet per second to 30 feet per second, you have a change in velocity of 10 feet per second. And if you said you went from 20 feet per second to 30 feet per second in 5 seconds, you changed 10 feet per second over 5 seconds. So you changed 2 feet per second squared. And that's acceleration. Now, gravity is, of course, an object that pulls things towards the center of the Earth, and it also creates an acceleration. Gravitational acceleration is pretty much basically the same wherever you are on Earth, as long as you're relatively close to the surface and not like way out in space or something. And that is either 9.8 meters per second squared if you're using the metric system, or 32.2, I like to add the decimal on there, 32.2 feet per second squared if you're using the US system. Now we're going to call these negative just because they're pointing down. Things are accelerating down, and we're going to call that the negative direction, or we're going to call up the positive direction. All right, so let's take Fearless Fred, who knows no fear, and put him on an airplane here. So he looks like he's having a great time, folks. He's on the airplane, sitting on the wing, and he decides he's going to jump off. Now, since the acceleration, the gravitational acceleration is 32 feet per second squared, after 1 second, we take 1 second times 32 feet per second squared, and we get 32 feet per second. After 2 seconds, so 2 times 2 seconds times 32 feet per second squared is 64, and you see that it just accelerates as we go 3, 4, 5 seconds. It keeps going faster and faster. We're not going to worry about air drag here. In real life, eventually, you'd get enough air drag that he would level out at what's called terminal velocity. But for our purposes, we're just going to assume that he keeps going faster and faster. There goes Fred. Look at him go. All right. So Fearless Fred, who knows no fear, has decided skydiving is a little bit too tame for him. He's taken up a new hobby. Nice. He's a human cannonball. So he's going to be a projectile. And we talked about what a projectile is. A couple of important quantities here. So first, the angle he's fired at matters. What is the angle from the ground to the path he's fired on? We're going to call that theta. That's this circle with a line through it. All right, that's the angle. Also, how fast is he fired? How much energy does he come out with? How much gunpowder was in there? What is this velocity? We're going to say this is his initial velocity, or V sub I, because that's the velocity he has initially on leaving the cannon. All right. So let's start out. We're going to point the cannon straight up. So we're going to have a theta, an angle of 90 degrees. We fire Fred, and we'll say that when he first exits the cannon, he's going 128 feet per second. Now, which way is gravity pulling him? It's pulling down. So he's traveling up, but acceleration of gravity is pulling down. So the gravitational acceleration is actually slowing him down. So he starts out 128 feet per second. After 1 second, he's lost 32 feet per second, so he's at 96. After 2 seconds, 64, he lost another 32 feet per second. After 3 seconds, he's at 32 feet per second. At 4 seconds, he's at 0 feet per second. For a brief moment there, he's stopped traveling up, and he's getting ready to start falling back down. Now, we take over right here. Here's our 4 seconds again. He's at 0 feet per second. Gravity continues to accelerate him down. And now he's also traveling down, so he's going faster and faster. So when he was moving up, gravity was accelerating down, and he was slowing down as he went. Here he's traveling down, and gravity is accelerating him down, so he's going to go faster and faster as he falls. So 0, then 32, 64. And you'll notice that this part is actually the same as when he fell off the airplane wing. Each second he goes further and further. And notice the distances here. After 1 second, he's only gone a little distance. After 2 seconds, a bigger gap. 3 seconds is a bigger gap. 4 seconds is an even bigger gap. All right. Now, let's imagine we had a big switch and we turned off gravity for a second and we fired him just horizontally. If we fired him at 128 feet per second, he would go from 0, the first second he'd go 128 feet, the next one he'd go another 128, another 128. So the velocity horizontally actually stays constant because there's nothing changing the horizontal direction. Gravity only pulls up and down, and if we're ignoring air friction, there's nothing to make him go faster side to side or slower side to side. He's just going to keep going at the same speed. When we add the two of them together, so when I add this, little gap, bigger gap, bigger gap, bigger gap, and constant distances this way, what we get is actually a parabola. All right, so this is what would actually happen if the cannon was, say, sitting on top of a cliff and you fired him. He would go a certain distance horizontally and fall a little bit, then he'd go a certain distance horizontally and fall even more, and fall more and more. And we see a vertical acceleration. So the vertical speed is constantly changing, but the horizontal speed stays the same. That's why we get this parabola. Now, if we put the cannon on the ground and fire him at an angle, we also see a parabola here. And there's a few different ways of writing the equation here. So I want to point out a couple of them. So this is the first one. The angle he's fired at, our theta, that's right there. This is our g value, which is either going to be negative 9.8 or negative 32.2. So notice we say negative 9.8, so it just be 9.8. And the x value is how far he travels, what we call range. All right, so that's from where he's fired to where he lands. I'd like to point out throughout this entire thing, Fearless Fred, who knows no fear, has never opened his parachute. The initial velocity is right here. So if I knew how far I wanted him to fire and I knew what angle the cannon was pointed at, I would plug those in. So here's the angle of the cannon. If the cannon was pointed at 20 degrees, I would say 2 times 20 degrees, and I'd have 40 degrees here, and this would be the sine of 40 degrees. And on the top, we would have, let's say we're measuring in feet, so I'd have negative 32.2 times however far I wanted him to travel, take the whole square root of that, and I would find how fast he needed to be traveling coming out of the cannon. If instead I knew how fast he was traveling, and I knew the angle and I wanted to know how far he was going, I would rearrange the equation. This equation and the previous equation are exactly the same, they're just rearranged. So here, if I knew the initial velocity, I knew the angle, I knew the gravitational value, I could find how far he would travel. All right. If instead I knew how fast he fires out of the cannon, and I knew how far I wanted him to travel, and I wanted the angle, I would use those values, find this number, take the inverse sine of it, and that would give me 2 times the angle. And then I could actually just divide that by 2, of course, and find the angle itself. All right, so that's how I can find these distances. Now, I do want to point out something. There actually are multiple different angles here. So, for example, if I calculated theta and I got 20 degrees, That's fine. 20 degrees will get you here, but actually, if you take 90 minus whatever angle you get, that angle will also work. So 20 degrees will go the same distance as something fired at 70 degrees. Something fired at 40 degrees will go the same distance as something fired at 50 degrees. And you'll see where those actually converge is at 45 degrees. And 45 degrees, if we subtracted 45 from 90, we would get 45 again. So 45 degrees, there's only one angle that would travel the same distance as something at 45 degrees, and that is 45 degrees. And that's actually the maximum distance. So if you want to find what the maximum distance you'll travel is, you want to fire at 45 degrees. And the reason for that is actually right here. If I'm trying to make the largest range, the largest X, and I am not changing VI, I'm not changing G, I want to make sine of 2 theta, the largest number. Well, the largest number you can have is the sine of 90 degrees. That's just 1.0. So if I want the sine of 90 degrees, well, what can I multiply by 2 to get 90 degrees? 45. So 2 times 45 here gives me 90. That would be the sine of 90 degrees. And then that gives us the maximum value for X. So firing at 45 degrees will give us the greatest distance. All right. So that's how we calculate how far something's going to travel based off of the trajectory equation.